Before starting the presentation, I just want to take 2 minutes to talk about who we are, what we do, very quickly. So we are a subgroup of ISPRS, which is the International Society of Photogrammetry and Remote Sensing. It's a non-governmental organization. It's dedicated to the development of international cooperation in our beautiful field in remote sensing, geospatial information. It's an umbrella organization, meaning that we collaborate with many different professional institutions and society across the world to develop remote sensing, networking, and the science. And as the Student Consortium, we are the official representation of ISPRS. So we work with the students and the young professionals in order to link them together, cooperate across the world, and make advocate imaging into spatial science for to be better for everyone. So this is us. It's the board of directors. There's Lakshmi that is also here today. It's our president, Nicholas Ticino, which is me. I'm the vice president. Tanni, editor-in-chief. Then we have Yogander, website administrator. Miguel, social administrator. And Chukubuma as a board member. And then, of course, we have also our volunteers that help us a lot, like Charan, Derek, Timus, and Charles, as graphic designers and proofreading. What we do is newsletters every now and then. Basically, we aim to publish 4 issues every year. We organize this newsletter. There are 16 published volumes so far. Well, the most recent issue is about the use of social media data in geospatial analysis. It's the one here on the top left. And then there is going to be an upcoming issue if you're interested in applications of underwater remote sensing. Stay tuned. We organize interviews and spotlight articles of research in this field. And then also, of course, we organize summer schools across the world and other events like GeoMixers, webinars, of course. And GeoMixer is just a catch-up around the world of students sharing the same passion like you today. And also, the last thing is coming soon is the student chapter. So if you're interested in launching a chapter, a small subunit of ISPRS Student Consortium in your institution, in your regional area, let us know, because we are very close to finishing up with the guidelines and all the regulations so that we can spread ISPRS Student Consortium even in your local areas. And to stay updated, if you're not already, join our social medias and become members. It's free. You can keep in the loop, and you're close to us. That's it. So today, as a speaker in this webinar series, we have Martin Brandt, associate professor of remote sensing at the University of Copenhagen in Denmark. Martin earned his PhD from the University of Bayreuth, I think Germany, in 2014, and is now associate professor at the University of Copenhagen. His primary areas of expertise encompass remote sensing and physical geography, focusing on the monitoring of vegetation dynamics, particularly in Africa and southern China. Notably, Martin's groundbreaking research includes the publication of more than 20 manuscripts in prestigious Nature and Science journals since 2018, and with 5 of them as a fourth author. Then, this is very recent and very good. A significant contribution to this field is evident in the recent Nature publication, where it pioneered the application of deep learning on a vast dataset of sub-meter satellite images, mapping billions of individual tree crowns in assumed free tree desert areas. In recognition of his outstanding work, he was awarded an ERC starting grant and a DFF Sapere Aude grant in 2020 to investigate trees beyond forested areas on a global scale. And that's it. Thank you very much, and we look forward to our active participation. There you go.
Yes.
Martin, the floor is all yours.
Thank you. Oh, it's working. Can you see my screen?
Yes, we can. Thanks.
Okay, I will turn off the camera so you can have a better view on YouTube.
Yes, thanks. I even forgot myself. Thank you.
Okay. Yes, thanks, Nick, for inviting, and thanks for attending. I will today talk about our work. So it's not only my work; it's the work of a large group. Yeah. So we are a group of a lot of people. We are PhDs and postdocs, around 15 people, all working in Copenhagen, and we are all doing similar things. So it's a big advantage of having many people who are working on the same things, to share, to exchange, and to collaborate on a certain topic. And what unites us, what we are all doing, is we are all mapping trees, and we are all doing this for large areas. And we are mapping with as many details as possible. So this is our work summarized in one sentence. Mapping trees, we are trying to do it large scale, and we are trying to map as detailed as possible. And this example below, or this example here showing, is a good example to illustrate our work just in one image. So why should we map trees? What is the motivation why we are doing this? Trees are extremely important. Trees are carbon stock. They mitigate climate change. They have high values. They have economic values. They have ecological values. And all these things, they are normally assessed via field works. Normally you go to the field, you measure the carbon stock, you measure the size of the tree, you assess the species, and you see what is the value of the tree. So why should we use satellite images if everything that we want, if this can be done with fieldwork? Normally, if you do fieldwork, they are plot-based. So you have to go there and you just make one plot, but you cannot really scale it. It's very time-consuming, so it takes a long time. You have to drive there, you have to go to the areas, and it takes really a long time. With satellite data, you can do all these things for very large areas. You can scale your work. You can go over a country or even a continent or the whole world. So what is the problem? Why is it not so easy to use satellite data to map all these nice things about trees? Well, it's especially there's tree cover can be mapped. Tree cover can be mapped, but if you go beyond tree cover, then it's really difficult. Mapping carbon stocks, mapping species, and mapping single trees is very difficult with current data. And here you see the Hansen data global tree cover set. And it maps something here in these areas, but it also misses a lot of trees here, which are scattered here in this area. So it's also very unreliable. And why is this the case? So if we look at Landsat-based products, this is a Landsat pixel. And then if this is a forest here, a closed canopy forest, this can be mapped. So this is a forest here, and this is no forest. And this is maybe half forest. So these things, they can be mapped very well with Landsat. But what if the area looks like this? What this is again a Landsat pixel here, and what if the trees are scattered? The Landsat pixel it will quite fail here. It does not really know what to map in these areas. And now really large areas of the world, they have scattered trees. So the green areas are the forests. In forests, the mapping, it works relatively well. But what about all the other areas which are yellow, light green? These are all areas where trees are scattered. So this is here in Senegal. And it looks like in these global maps, it looks like there are no trees, but this is not the case. So if we zoom in, there are a lot of trees in these areas here. So what we wanted to do something, what is the way forward to improve this kind of mapping is to use very high resolution images. So going away from images like Landsat and Sentinel, where you see basically only the forest areas, we want to use high resolution images where you can see single trees. And we're using not the classical decision tree models, but now we're using AI models, it's deep learning. And the first milestone we achieved in 2020 when we mapped 2 billion trees in West Africa. So this was the first time where a large amount of very high resolution images was used and together with deep learning techniques. And then we mapped the trees at the level of individuals. So we didn't map anymore a pixel area, but we mapped at the level of individuals. And that was an area of a few million square kilometer and 2 billion trees. So it's really impressive numbers. And that was the first time we really got a lot of attention for our work. And then 3 years later, now in 23, we expanded. And then we mapped not 2 billion trees, but now 15 billion trees. So we expanded over the entire Sahel and Sahara area. It's not just West Africa, but we went the whole way to the Red Sea here and mapped 15 billion trees. And again, like the other paper, this was again published in Nature. And why was this another time published in Nature? Just by expanding the area. No, this time we attributed carbon stocks to single trees. So we made a viewer, and you can basically zoom in everywhere, and you can click on a single tree, and then it will tell you the carbon stock. So it will whole carbon stock, the root carbon, wood carbon, and leaf carbon. And that was also very, very detailed and very large area. So now we basically see trees from a horizontal perspective. This is where the satellite image is recording the trees. But now we want to add, and this is what we did, we want to add more perspectives, a vertical or a volume perspective. So vertical perspective is the canopy height, where you can do with LiDAR, and the volume perspective is then going towards biomass, and this is normally done via field data. And how did we do this for this study in Africa? We collected a lot of field data, which included both the biomass and also the crown area. And then we estimated from the crown area, which is basically what we see from a horizontal perspective. We see the crown area. And then we established some relationships between the biomass and the crown area. And that we had field data for wood mass, for root mass, and for the leaf mass. So we established different relationships to estimate the biomass via the crown area. So normally biomass is estimated per unit area. You have an aggregated value, a reflectance value from the satellite image that you relate with the biomass. But now we do it the other way. We first map the trees, we attribute the biomass to every tree, and then we aggregate. So we go from the tree level, and then we aggregate to larger units like a hectare. And then we also have the biomass per hectare. But in our case, it's not the starting resolution. Other studies, they start maybe at a hectare resolution, but for our case, it's the aggregated resolution from the tree level. This is the area in Senegal, just to illustrate how this looks like when every tree has a different color, which is the biomass in the trees. But it should be easy in these areas where trees are separated, like in West Africa, in the Sahel area, trees are scattered, and it is relatively easy to map them. But what is if it looks like this in the rainforest areas? So would this also work in these areas? So we have a PhD student, Maurice. He is working in Rwanda, and Rwanda has this nice many situation that you have many ecosystems. You have savanna, you have plantations, farmland, and you have also rainforest. And he did a similar thing that we did for the Sahel area. He did for Rwanda, which included also rainforest. And we had a lot of field data for Rwanda, and it was relatively close to the field data what he was estimating from his approach. And then the nice thing is, if you have images over several periods, you can see changes at the tree level. And that is also what Maurice did in Rwanda. So we can have a 10-year period. With a 10-year period, and in this period, you can see the growth of single trees. Like here in this farmland, you can see how many trees have been planted here in this farmland. So here in an area of a degraded forest, you can see how many trees have been growing here in 10 years. And then you can estimate the carbon stock of the trees that have been growing. So we move again to another area. Now we go to Northern Europe. We go to Denmark, Finland, and these areas. And now we want to do some innovative approach. So of course, it's possible to get the biomass from the ground area, but it's so moving from the horizontal perspective to the volume perspective using allometric equations to convert the ground area to biomass. This is possible. But now the idea is to let the CNN, to let the deep learning model automatically find this relationship. So what the idea is, we show the model the image. It's the RGB image. We just show the image, and at the same time we give some information on plot-based biomass. So it's 30 by 30 meter, and then the output, we want the model to give the biomass at the plot level, 30 by 30 meter. So the model should automatically learn the relationship between biomass and the optical image, and it works. It works actually very well. So this is a plot. This is a plot-based biomass, and this is the RGB image, and this is the output. So it gives us per plot the biomass. And if you compare the estimated biomass with a test set that was not used for training, so it's completely independent data, then I think it works surprisingly well, considering that the model has no information on height or no information on any other features. It just sees the image, and it can estimate the biomass from seeing the image. And to illustrate what the model is actually seeing, we show here activation map. So the model sees what it gets for training. For training, it gets the RGB image, and then the plot-based biomass. So it gets one map value here, and then we illustrate here what the model sees. So this is not the output map. This is the activation map, which is illustrating how the model is learning. And it shows that the model actually learns where are the trees. So it really can find where are the trees and where is the biomass. And this information the model has never seen. The model only knows the 30 by 30 meter biomass as what it shows per output. But it can actually learn automatically how the biomass is distributed among the trees. And that is I think, quite surprising. So we're doing all these things for Denmark. Denmark is a nice area where you have a lot of different forests. We are doing this for deciduous forest, for coniferous forest, also for non-forest trees, biomass estimations, tree counting, tree count segmentation, biomass mapping. But then the question is, of course, why should we do these things for Denmark? Because Denmark is not a country like in Africa where you have like Senegal, for example, where you have most of the trees outside forest. But then if you do this mapping, then you actually see that many trees are growing outside of forests, also in Denmark. So from this mapping, we find that 30% of the trees are growing outside of forest, and that is then a number that is basically not measured from the national forest inventories, and these trees, they are also not included in existing tree cover and biomass products. And this is already a bias, a number which is quite substantial. Moving further to other countries, I'm currently in China, and so I also do work in China. China is in southern China, the landscape is extremely challenging. We have the karst area. We have a very complex landscape, so we really want to stress the model to learn in the most difficult environments. And again, it works. So we are able to segment tree crowns. I don't have a lot to show here because it's relatively new. Also, we are doing some other approaches, but tree crown segmentation is done, and this works very well, even though it's extremely challenging. And then we also want to add. We always want to add some new approaches, not just doing the mapping again. In this case here, we have this challenging landscape, and a lot of forests and trees in China, they have been planted over the last 20 years, and now we want to study a bit, to use these segmentation data to study the complexity and the structure of the forests. And then so we look at the single tree counts, and then for every tree we search for the neighboring tree and calculate the spacing of between the tree crowns and the angle to other trees, the distances to other trees, to estimate a kind of complexity of the distribution of the trees. And you can see this is a plantation on the right side, and it's a secondary forest on the left side. And there are very big differences between plantation trees and real normal forests in all these parameters here. Then we are not only mapping trees as binary, but we also want to know a bit about the species. And so we trained a deep learning model over the Sahel area to map the baobab tree, which is a relatively characteristic tree. So it has very interesting shapes, very interesting shadow, and it's possible to train a model that can identify this specific shape in the satellite image. So we mapped a few million baobab trees, or the location of baobab trees for the entire Sahel area. And then all these things are nice, but it's all based on data which is relatively difficult to acquire. It's expensive or cannot be repeated over several years. It's the sub-meter images that we used. So we were searching for solutions which we can scale to global scale and which we can also repeat in time. So we don't only want to do it one time, we want to have frequent measurements like yearly or even more often than yearly. And so we found the planet scope images. Planet is PlanetScope or Planet DAF are the satellites called. This is a DAF satellite and it's very small. You can hold it in one hand compared to a worldview satellite, which is very large. And so the images, there are more than 200 planet satellites, planet DAFs, and they record the entire world every day at 3-meter resolution. And that is something that sounds extremely attractive for us. You have a high resolution and you have a daily coverage of the whole world. And the 3-meter resolution is not sub-meter, it's not like 50 centimeter, what I showed before, but it's not so bad. So we can see here the comparison Landsat, you see basically nothing. And Planet, you can see the single trees. You cannot see too much details, but you can see the single trees, even down to relatively small ones. You can still see them. The comparison, so SkySat is sub-meter images, is similar to worldview, is 80 centimeter. Then the same area, PlanetScope, you can still see that the trees are visible. The very small ones here, the tiny ones, they become invisible, but the normal sized ones, they are still visible. And then the same area with Sentinel, the trees, they are not visible anymore. So you have 80 centimeter, you have 3 meter, and you have 10 meter. And you can see that 3 meter is still okay, but when you go to 10 meter, the single trees, they disappear. So looking at what you get and what you lose with different resolutions, optimum is of course the field data. You have all trees. Then you're moving towards the sub-meter data like SkySat or MaxSat satellites. You lose the understory. We cannot see the understory anymore. Then moving towards the planet or nano satellite images, you're losing the small trees. Moving towards Sentinel, you're losing individual trees. Moving towards Landsat, you cannot see the structure of the vegetation anymore, only large areas. And then moving even more to MODIS and other coarse data, you only see aggregated values, but have no information anymore on the structure of vegetation. So we were excited about the planet images, and we bought 400 million square kilometer, which covers the whole world a few times. And we divided the world in grids, in 1 degree grids. This is how a grid looks like in Africa. It consists, 1 by 1 degree consists of maybe 100 single raw scenes. So we have a downloading, we have automated all these in frameworks that download the images and create the mosaics, adjust the colors to each other, and then with these mosaics we are working. So Florian, he did the tree mapping using PlanetScope images for all Africa. That was the first large-scale application. It's the same model that we used before for the sub-meter images. We used now to segment trees in Africa with using PlanetScope. And the difference is that single trees, they are mapped as individuals, but if the trees form closed canopies, then we just map it as a solid area. Then we cannot distinguish anymore between single trees. And then we also want to go beyond tree cover with PlanetScope. We don't want just to make a tree, no tree, but we want to estimate height and biomass. And that we did for Europe. So we trained with airborne LiDAR the height, and then we converted using field data the height to biomass. So the planet-based mapping of height will be converted to biomass, and then biomass per hectare ideally includes also the small trees outside forests. So we did this for all Europe. It's already published. So you can see this is the PlanetScope image. This is the LiDAR at 50 centimeter, and that is the prediction of canopy height from planet, and it's very close to the LiDAR. So it comes really close to the LiDAR, and LiDAR is very expensive, and the PlanetScope images are not very expensive. So we estimated biomass for all countries in Europe, and we compared with national inventories for 30 countries. and it matches extremely well. So our estimates, they come extremely close to the national inventories from these countries. And we were even surprised how close this comes. And then another work what we are now doing is to add a temporal component. So it should not just be a one-time mapping, but now we want to add the dynamics. So with Planet starts in 2018. So we can map every year we can map the trees, and then in the next year we can see if the tree is still there or if it has been removed or new trees are growing. And this we did for India. So India is a large area, and we used Rapid Eye for 2010 and 2011, and then Planet Images for the last 4 years or 5 years, and did this only for the farmlands, so not for the closed canopy areas, but only for farmlands where the trees are relatively large and where the single trees can be mapped. And then we found where trees have been removed. So in this example here, the red points are trees that have been removed over these 5 years. And the green ones are those which have still been found in all years. So here we are, I'm not talking too much about methods. Here very small method slide. So it's a planet image, and then we are using a deep learning algorithm that is predicting a heat map. So that is the heat map. It's trained with points. So we make a point on every tree for the training, and then we're predicting a heat map, which is Gaussians. And these Gaussians, the peak of these Gaussians is then the tree count center, and that we can then use to track the tree. So the example here, 2018 and 21, is this two images, and the heat maps, which is the prediction from the tree counting. And then we see the red points are trees that have been lost or disappeared over this period. So we can then see that there are some trees that have been disappeared. You can see they are not here, but they are here. Or so for a larger one, there's a tree here that is not there anymore here, and that is then shown as a red point. And it's very interesting to map these changes, because it's, even if it's a relatively short time period, we found millions of trees in India have disappeared. It's a large area, so it sounds dramatic, but it's also over a very large area. But there are some hotspot areas where you really have many trees that have locally disappeared over a short period. Like here, 2019 and 2022, it's a relatively just a few years, but you can see that many of these large trees here, they are not there anymore. Sorry, they have disappeared here. Many of these large trees here in this area. And then continuing the work, what we're also doing is mapping in cities. So we have mapped a tree cover. Now it's not single trees, but it's tree cover for all cities in China, which is also being expanded to a global scale now. And again, the interesting thing is to repeat it over several years. So we did this for 2010 and 2019, and looked for changes in the Chinese cities. And a lot of trees have been planted in Chinese cities. The interesting thing is that it has mainly happened in the large cities like Shanghai, Beijing, Shenzhen, but in the smaller cities, not much has happened over this 10-year period. Then we don't just want to map trees and publish scientific papers. We're also very interested in having our methods and our data being applied in the real world. So last year, a whole group, we went to Rwanda, and we introduced our tree mapping in Rwanda, and it's also implemented now in national monitoring in Rwanda. And this year we were in China. I'm actually still in China. The others have already left. And also in China, we presented our work at several institutions to exchange data and to raise interest in the mapping of single trees. So it's a relatively large group. This is the core tree mapping group. We traveled around in Africa and in China, and what I presented today is a summary of what many people are doing. So it's only works because everyone is contributing and exchanging. And we still have a lot to do. So we have already mapped a lot, and but getting what we did consistent, adding a kind of consistency and making it operational, adding a temporal component at very large scale, there is still a lot of many challenges to be solved. And that was my presentation.
Thank you, Martin. It was very, very inspiring, very amazing science that you and your team are doing in Denmark, but it's really an international team that you're collaborating with, and very good. So also this mix of it's very nice, in my opinion, when a team can share a lot of knowledge towards one big common goal, which is mapping trees. So we have some questions. We have some questions from the audience. I'll start with one question from Manikandan that asks how individual tree crown are delineated from dense forest.
There are several things. The first thing is the meaning of delineating tree crowns in the dense forest is often questioned, because why would someone want to know single tree crowns in a forest? And it's also because you miss, of course, the understory. We cannot estimate the understory. So we still do it in some cases, but in many cases we also go away of the delineation of tree crowns in the closed forest. But try to estimate. I didn't include this in the presentation today, but we try to estimate many things at the kind of plot level. Of course, the model, the CNN model, the deep learning model, like I showed, it still sees the high resolution, so it can still see the single trees. But the output in the end comes at the plot level, where you can use the information like biomass or tree count and these things. But nevertheless, it's still possible to delineate large trees in the forest. You can do it visually. You missed the understory, but you can delineate the large tree counts. You can do this. And then the interesting thing is to repeat it, and then see if the trees have disappeared over a period. Then you can see selective logging, and then it makes also sense to map single trees in the dense forest if you start repeating this. Yes, it's a relatively long topic, and I could talk a long time about this, but maybe I will not continue.
Good. Thanks for the answer. We have other questions quickly from Kolech Albel. Is your model capable of identifying the specific tree species, wood density, and other relevant tree characteristics, given that tree carbon measurements exhibit sensitivity to these factors?
Species mapping is of course challenging, because it's if trees look very specific, if they have a very specific shape or some special leaves, then you can map the species, but otherwise you cannot. But there also, of course, species are important for estimating the biomass, but if the training data includes, like if you have plot data and the information on the biomass is included in the model, and the model it does not care about the species itself, but what it learns includes information about species, about understory. All this information is basically learned by the model, and the model can then predict at the plot level the variables that we would like to know, and the species. So what we now try to do is not to go the way like identify the tree, identify characteristics like species, like height, like biomass, and then or like these things, and then have this information per tree. But we would like the model to learn all these things by itself, and the model can basically then maybe it can see the species from some information, maybe not, but it will be able to relate the target variables with what it sees. That is what the approach we are currently working on.
Interesting, thanks. Then another question from Marcio da Silva. Great presentation. How do you build a training dataset where understory, grasses, etc., shrubs, again, are within the trees? Have you done any work in Australia?
Australia is on the way. Yeah. It always depends on like outside of the forest, you don't have so much understory, and the trees are scattered, and you don't need to worry much about these kind of things. Just map the single tree, and you can attribute some biomass values or whatever. In the forest is different. We are using plot data or field plot data. We have NFI data in Denmark that we're using to estimate either how much do we miss, how much is the contribution of understory that we are missing, or we try to add it to correct the bias, or we try to let the model learn automatically to include this missed information in what it learns. So it depends a lot on the area. Or with perennial grasses, maybe also mean that the trees are not so easily visible. And in this case, we are selecting images. It's actually the shadow. It's the shadow of the trees that is very characteristic, and grasses don't throw a shadow. So even if the grasses are very green, you can still distinguish the tree because it throws a shadow. And we are trying to use images from the early morning where the sun is still low, and then the shadow is very clear in most cases.
Thank you. Thank you. And regarding Australia, we are working on that, myself actually, and Martin and his team. And yes, we are about to train a model to work in the whole Australia as well. We're using LiDAR, using UAVs, and for aerophotogrammetry. And yes, in forest is pretty difficult, especially the dense rainforest. Another question from Amin. Many thanks for showing this bright work. I have a question regarding the upscaling of these results to medium resolution sensors, like Sentinel-2, which might allow frequent and timely monitoring. Do you think that using the state-of-art image unmixing technique, we could reach good results to upscale planet finest maps to these sensors? Thank you.
You can do some super resolution and sharpen the Sentinel images to get a higher resolution on, but it will never reach the original quality. So it's not the same 3 meter and 10 meter. So the information you can of course estimate it, but it remains an estimation. While with Planet, it's really you see the features, and it's always not the same to see the features and to estimate them from some values. It's possible, but it's not the same.
Okay. Good. How are we tracking with time? Okay. Yeah. Give me a second. There is one other question. Jaydeep Day asked how to segregate individual trees from LiDAR data.
That is for you.
Yes. Do you want me to answer?
Yeah.
Well, I can tell you what we are doing from LiDAR data. It depends. There are many approaches. The quickest way is to rasterize the LiDAR into canopy height model so that you can apply segmentation techniques. There are various algorithms that do a segmentation technique on the canopy height model. There is one very good that is called Dal Ponte. It's a Dal Ponte 2016 algorithm that takes a layered approach and create a good brown polygon dataset, if you want, from canopy height models. But the reality is that that really depends on the resolution of the point cloud. If it's coarse, you might need to do that. If it's dense, like with UAV, you might want to take a bottom-up approach using ray tracing algorithms that shoot rays from the bottom up and reconstruct individual trees, geometry, trunks, branches, and leaves all together. And that's very computing intensive, but that's what you can do. Or use convolutional neural network, 3D convolutional neural network, to segment individual tree from point clouds. But it's a big discipline by itself. It's a huge topic. I would like to ask, Amparo I would like to ask if how will the society benefit from your study of large-scale tree mapping?
It's a very broad question, and I can just pick a few without answering, giving complete answer. I can pick a few aspects which I think is interesting. Like if you have some smallholder farmers, or let's do it differently. Let's say trees that were invisible before, they become visible now. So resources which no one knows about, we can now map them and we can track them. Like examples are smallholder farmers in like, let's say we did the study for Rwanda, where you have millions of trees. It was actually, I think, 100 million of trees have been planted by smallholder farmers in the last 10 years. And in these numbers, they are no one knows, and now we know it. So we can basically exactly or not only map them but also estimate the carbon that is the carbon sink from these trees that have been planted by some smallholder farmers, or if trees are removed, or if, in the forest, outside forest, or if trees are planted, we can track it and we can quantify it. And it's a lot about carbon these days, carbon credits, and a lot of these natural regeneration is not happening in the forest but outside forest, and there's no monitoring technique, and now we have it to map and monitor tree restoration and plantation. I could continue on this, but I think this is the most important.
The most important point, yes, you covered it. Okay, and there is Amparo, the same person, is also asking how hard it is to do tree mapping in the Philippines, how to prepare myself if I plan to conduct a thesis related to it. I have some extra hands in the Philippines.
Philippines, I know that is covered with aerial images and LiDAR, or most parts of Philippines. I saw this somewhere, and basically it's not magic. If aerial images and LiDAR are available, then it's about delineating by hand, or trying to delineate automatically from the LiDAR, depending on what works better, and then running the models. So if a GPU is available and the images are available, then it's no magic behind. The codes, they are all online, so they can be downloaded, and it's then drawing the tree counts, running the detection, repeating until it works.
Thank you. Angie's Budders ask, is it possible to use this data also for species detection or tree age identification?
Yeah, if the resolution is extremely high, like if you have a really high resolution, then you can see the species, they have a specific shape. Otherwise, you can try to make use of the temporal information, like in Senegal or in West Africa, the Phyterbia albida has no leaves during the rain season, and it's the only species which has no leaves during the rainy season, and you can train a model that searches directly for these trees without leaves. Tree age, you can always try to estimate from the size. You can assume a smaller tree is a younger one, but its uncertainty is very high for the age.
Actually, I have a follow-up on this topic. especially because you showed your work in India where you could detect missing trees from one year to another. What about the other way? What would be the minimum height that is detectable using heat map approach on planet so that we might monitor tree growth or tree plantation?
I think the key for the growth is to have a lot of images and predict on many images and then look for the change. Even if it's the tree is hardly detectable, but you would see some change of the heat map, the confidence would increase over the time. So even if the single tree is maybe not detectable, the confidence increases if the tree grows. But you need a lot of images and predict many times, and then I think it's possible even with small trees that are visible. So Florian, he tried, and it's possible.
Yes, he showed me something. I'm asking because we're also having this decision to do to what is a tree. Another interesting question is how you define a tree, because there are many different definitions across the world, depending.
Yeah.
Even legislators define a tree differently than forestry people.
Yeah.
Or what a tree for you? What is a tree for you?
Yeah, it depends on the data that is used. No? So it's a tree is what we can detect with the data, and the better the data, the more we can detect. So from the forest inventory in Denmark, they assume everything above 1.2 meters is a tree, and then that is like a flower in our garden. So that is a larger flower, and that is not, of course, will never be possible, or not in the coming 10 years to detect with a satellite. But with 20 centimeter, you can really go to smaller ones. But then with Planet, you cannot. And then this it really depends on the data set you're using to say what is the tree in this. But it should have a shadow. So if we cannot see any shadow, then we also do not map it.
Interesting, yes. A remote sensing definition of tree.
Yeah,
I see
everyone has a different.
CJ. Yeah, of course, it's functional. CJ, you're raising the hand. If you have a question, pop it in the chat and I'll read it. Okay. I think we are done, unless CJ wants to write a question or you just have the hands up. We ran through all the questions. So thank you. Well, I think we can end it here. Thank you very much, Martin, for your presentation, for showing us your beautiful research. And thank you all of you guys that attended this webinar today. Please follow our social networks for other occasions, for other webinars in next year, especially in the next year, and also our newsletter that we are organizing right now. Martin, unless you want to add something else for like a piece of wisdom for these young researchers that attended your webinar. You're all good.
The young researchers are very happy to have this huge choice of data and these fantastic methods that 10 years ago we had to work with 8 kilometer pixel size. And now you really have the chance to work with data where you can see the objects, and that's really a great thing.
Yes, we are spoiled, especially the younger ones. They're spoiled with data, good data to play and work with. Okay. Thank you, guys. Thank you again, Martin. We keep in touch.
Yes.
I'll see you next week, and I'll write you an email. Okay. Thank you so much. Bye. See you, Martin.
Bye-bye.
See you, everyone.